tutorial, we're gonna look at covariance and describe how covariance can be used to describe the shape of a data set, as well as show its geometrical relationship when using and working with linear transformations and eigendecompositions. Okay, so let's start briefly with variance. So, so what is variance? Variance does measure the variation of an individual random variable, like for example a person's height with respect to population. And this can be described as follows. Given that we have a number of n of samples, say a number n of people, persons, then we can say, okay, xi might be the height of an individual person minus x bar being the mean height across the population. And so summing over the square differences here multiplied by this constant in front, we get the variance sigma squared. The covariance, on the other hand, describes how two variables do vary together. So, for example, this could be the height of the person as well as the weight of the person. So again, we would have a sum over the population size and would multiply the differences from the mean of, say, for example, here for a single person I, the height difference multiplied by the weight difference, again multiplied by this constant in front. And what we can see as well is that actually the variance is a special case of the covariance, if you will, if we have the same variable here. So x times x, that would be sigma squared, would be the variance. Okay, so now we can build up the covariance matrix. So we have a data matrix X, and this data matrix X is a matrix of n by d dimensions. Again, therefore we have a row per each sample, and then we have individual values, and therefore n times d. N represents the number of samples, and d the dimensionality of the vector per sample. Okay, and we can write this as follows. Again, we write the difference from the mean, and then we multiply this by the difference from the mean transpose. And we can also rewrite this in a way that we basically write it in short like this: x times x transpose defined by this offset, by this constant n minus 1. And what we get here is a semi-definite matrix. Okay, so, and I should say one more thing. So in this case, this is for the case of having a zero mean, right? So as you can see, this basically vanishes if this is 0, and then we get this results in x times x transpose. So I should actually mention that. Okay, so let's have a look at a very simple case, 2D case, which actually forms the basis for higher dimensional cases as well. But again, we can see on the diagonal we find the variance, that is x by x and x y y. This is actually sigma squared of x and sigma squared of y. And then along off the diagonal we get our covariance values. So actually the covariance matrix, sometimes called the variance covariance matrix, because it contains the variances of the data set as well. Okay, so Now let's look at this particular case. What we see here is actually a covariance matrix that on the diagonal has the variances of the data sets, two variables x and y, and on the off diagonal we see 0. So what that actually means is, if we were to draw this, we would see that actually here the covariance being 0 means that the two variables, in this case x and y, are actually independent or uncorrelated, and therefore we have these zeros here. And so let's have a look how we can use linear transformations or transformations in general to affect the data and therefore the covariance matrix. As an example, what we do is to transform our matrix using a scaling factor. And what you can see here, we got a scaling factor for x and for y, and this transformation would simply scale the components x and y by multiplying them with s, x, and s, y respectively. And therefore we can say that what we expect, given that this is a linear transformation, we can expect the covariance matrix C of the transformed data to look like this. So here we multiplied this scaling factor simply into the variance. And what that also means in turn is that we can actually formulate S as the square root of C. So turn this around and then we basically get S again. And that we transform, as I mentioned, the original data set S times X in order to get the data Y. Okay, so now let's apply a linear transformation in the form of a transformation matrix T to the data. And this T is composed of a scaling matrix, that previous scaling matrix that we've been looking at as well as a rotation matrix R, right? So, and these are multiplied to form this transformation, and the rotation is given here by the cosine of a theta and so on and so forth. Okay, and here theta is the rotation angle. And so what we then can do is to compute, as what we see here, compute the transformed data Y by multiplying it, the transformed data Y as T multiplied to X, the original data set. Okay, and now this, in order to solve this would lead to the question of how to decompose the covariance matrix into a rotation matrix and a scaling matrix. Okay, and so here we're gonna look at eigen decompositions of the covariance matrix. So generally, eigen decomposition represents one connection between linear transformation and the covariance matrix. And the general definition of an eigenvector is to be a vector whose direction does not change if we apply a linear transformation to it. And this can therefore be expressed as A times V is equivalent to lambda times V. So V represents the eigenvector of the matrix A, and lambda is the corresponding eigenvalue. So if we then put all eigenvectors into columns of a matrix V, and all the eigenvalues as entries of a diagonal matrix L, then we can now write our covariance matrix C using the following equation. And that is C times V is equivalent to V times L. And here the covariance matrix therefore can be formulated as C is equivalent to V times L times V minus 1. And that can be solved using singular value decomposition. The eigenvectors do represent unit vectors that give direction of the largest variance of the data, whereas the eigenvalues do represent the magnitude of this variance. And this denotes that V does represent the rotation matrix, and the square root of L does represent the scaling matrix. And so what we can do from this equation is to represent the covariance matrix as C is equivalent to R times S times S times R to the power of minus 1, right? So we've been defining our scaling matrix as square root of L. So square root of L times square root of L would be L again. So S times S, and R is equivalent to V. And here does represent the rotation matrix. And so therefore from our previous linear transformation, which was that T is equivalent to R multiplied by S, we can basically look at this and see that we have this R times S is equivalent to T, as we've shown earlier, and S times R to the power of minus 1 is T transpose. All right, so we got our definition for the covariance matrix back. And this is due to the property that R to the power of minus 1 is equivalent to R transpose. And this is true because R is orthogonal. And S is equivalent here to S transpose because it is a diagonal matrix. Now, in order to compute from the covariance matrix this linear transformation, we have to compute the eigenvectors from the covariance matrix C. And this is done as T equals V times square root of L, where we have V as the previous matrix with the columns being eigenvectors of C, and L is the previously shown diagonal or given diagonal matrix, which does consist of the corresponding eigenvalues. And we can now use the Cholesky transformation, where we have set is equivalent to L to the power of minus 1, and then x minus the mean of x, to compute the transformation matrix. And here L represents the Cholesky factor of C is equivalent to L transpose. And what we can also see is that the basis vectors of the transformation matrix well, actually we can evaluate the basis vectors of this transformation matrix by showing each eigenvector V multiplied by sigma being equivalent to square root of lambda. Okay, yeah, so what we've shown now is that we can now get the covariance matrix, form the transformation matrix T from the covariance. And we can also use an inverse of T to remove correlation from the data. So finally, an interesting way to use the covariance matrix is actually within the Mahalanobis distance. And that is used to measure multivariate distances using the covariance. So how it does is that is to compute uncorrelated distances between some point x to a multivariate normal distribution using the following equation. So here we got the distance, Mahalanobis distance of x is square root of x minus a mean transpose times c minus to the power of minus 1 times x minus the mean. So the mean represents the mean of this multivariate normal distribution. So in this case, for a Mahalanobis distance, we assume the points to be normally distributed, and c is denotes the covariance. And yeah, so this is how we can actually use covariance here to define this particular distance. Okay, so yeah, so finally looking at this relationship between covariance matrix and the linear transformation does actually is important because it constitutes an important fundamental aspect for the understanding using of singular value decomposition, PCA, Mahalanobis distance, as well as other topics in statistical pattern recognition. So yeah, so therefore hopefully you find that helpful.